The Disappearing Spoon and Other True Tales of Madness, Love, and the History of the World, from the Periodic Table of the Elements by Sam Kean. Picture yourself at an elegant dinner party, the kind with delicate china and gleaming silverware. You reach for your teaspoon to stir some sugar into your hot tea. The steam swirls upward as you stir, but then something bizarre happens. As you lift the spoon from the cup, it just melts away, right there in your hand, leaving you holding nothing but a handle and wearing an expression of complete confusion. Your host, a chemist with a mischievous grin, is trying not to laugh. Congratulations, you've just fallen victim to one of science's most delightful pranks, courtesy of an element called gallium. You see, a gallium spoon looks exactly like any other metal spoon, solid and dependable. But here's the trick. It melts at a mere 84 degrees Fahrenheit. The warmth of your tea, or even just the heat from your palm, is enough to turn it into a silvery puddle. This charming bit of chemistry trickery is actually the perfect doorway into one of the most remarkable storybooks ever written. And no, I'm not talking about some fantasy novel. I'm talking about that mysterious chart that probably gathered dust on your high school chemistry classroom wall, the Periodic Table of Elements. Today we're diving into an extraordinary book called The Disappearing Spoon by Sam Kean. This isn't your ordinary, sleep-inducing science textbook. It doesn't just catalog what the elements are, it reveals who they are. It shows us that the periodic table isn't some boring list of chemicals, but rather a vibrant tapestry of human history, bursting with passion, discovery, betrayal, and absolute genius. It's essentially a storybook of our entire world, where each element plays a character with its own tale of brilliance, madness, and everything in between. Sam Kean has sold millions of copies of his books, and The Disappearing Spoon has become a modern classic by demonstrating that science, at its core, is a profoundly human story. He was originally a physics major who discovered that his real education came not from endless equations, but from the stories his professors shared between lectures. Tales of explosive sodium being hurled into rivers, connections between Gandhi and Godzilla, scientists boldly experimenting on their own pacemakers. He realized that behind every cryptic symbol on that famous chart lives a story just waiting to be discovered and shared. So here's my promise to you, by the time we finish this journey together, you'll never look at the world quite the same way again. You'll see the elements not as abstract letters and numbers, but as the fundamental building blocks of both history and human character. You'll understand how a simple chart can explain the rise and fall of empires, unlock the secrets burning in the heart of the sun, and even illuminate the madness that drives both artists and scientists to their greatest heights. We're about to peel back the layers of the periodic table and discover an entire universe of stories hidden within its structure. Let's begin our journey where all great adventures start, with a map. The periodic table is essentially our map of the universe. At first glance, it resembles a somewhat lopsided castle with tall towers on either end and a long connecting wall between them. It has 18 columns and 7 rows, with an unusual landing strip of 2 extra rows at the bottom. Each brick in this castle represents an element, a fundamental substance that can't be broken down by ordinary chemical means. There are over 100 of them, and the entire structure of our reality depends on them being exactly where they are. The most fundamental rule of this map is beautifully simple. An element's location is its destiny. Where an element lives on the table tells you almost everything you need to know about its personality. Let's start on the far right side, in column 18. This is where the noble gases live: helium, neon, argon, and their relatives. They're called noble, for good reason. Think of them as the aristocrats of the elemental world, perfectly content in their own company. Here's why. Every atom has shells of electrons orbiting around it, like layers of an onion. Atoms are happiest when their outermost shell is completely full. The noble gases are born this way, naturally complete. Helium has 2 electrons, which perfectly fills its single shell. Neon and argon each have 8 electrons in their outer shells, making them completely satisfied. Because they're so stable and self-contained, they have absolutely no need to interact, bond, or react with any other elements. They're like the chemical hermits of the universe, incorruptible and serene. For this reason, they were actually the last elements to be discovered. Nobody even knew they existed until the 1890s, simply because they refused to associate with the rest of the periodic table's neighborhood. But this peaceful kingdom is surrounded by absolute chaos. Just one column to the west, in column 17, live the halogens, like fluorine and chlorine. These elements are the most reactive gases on the entire table. They're essentially the bullies of the block. Why? Because they have 7 electrons in their outer shell. They're just 1 electron short of that perfect stable number of 8. And they will do absolutely anything to snag that final electron. They'll beg, borrow, and most often violently steal it from any unfortunate element that wanders too close. Now, if you imagine the table wrapping around like a map of the world, where the far east meets the far west, you'll find column 1, sitting right next to the noble gases. Here live the alkali metals, like sodium and potassium. And if the halogens are bullies, the alkali metals are dangerously generous to a fault. They have just 1 lonely electron in their outer shell. All they want in life is to get rid of it so they can reveal the full, stable shell underneath. This makes them incredibly reactive. Some of them, like sodium, will spontaneously burst into flames if they so much as touch water. You can see the natural partnerships that form from this chemistry. An alkali metal, desperately wanting to give away an electron, meets a halogen, desperately wanting to steal one. It's basically a match made in chemical heaven. Sodium happily gives its electron to chlorine, and they form a powerful bond, creating sodium chloride, which is just the table salt you casually sprinkle on your dinner. This elegant dance of giving and taking electrons is, in essence, the entire story of chemistry. Atoms are constantly trying to achieve that noble gas-like stability, and their struggles, their alliances, and their epic battles create every substance we know. But not all elements are so straightforward in their behavior. In the middle of the table, stretching from columns 3 to 12, you'll find what's called the Great Planes, the transition metals. These are your familiar everyday metals: iron, copper, silver, gold, titanium. They have frustratingly complex chemistry. Unlike the elements on the edges, they start filing their electrons into inner shells, called D-shells. They essentially hide their extra electrons away, burying them deep inside. This means that as you move across a row of transition metals, adding 1 electron at a time, their outward personality doesn't really change much. The new electron is tucked away, shielded from the outside world. This is exactly why so many metals look and act remarkably alike. They're all cold gray lumps because their outer electron structures are nearly identical. They're the conformists of the periodic table. Then you have the elements in those 2 mysterious rows at the very bottom, the lanthanides and the actinides. These are the rare earth elements and the heavy radioactive ones. They bury their new electrons even deeper, sometimes 2 full energy levels down. This makes them almost completely indistinguishable from one another. Trying to separate one lanthanide from another is genuinely one of the most tedious and maddening tasks in all of chemistry. One dedicated chemist in New Hampshire spent years performing the exact same chemical process 15,000 times by hand, just to obtain a mostly pure sample of the element thulium. It's like trying to tell the difference between 2 individual grains of sand from the same beach. This architecture, the arrangement of electron shells, drives all of chemistry. But to truly understand the elements, we have to look even deeper, into the nucleus, the dense heart of the atom. And here we meet one of the most unlikely heroes in the story of science, a woman named Maria Goeppert-Mayer. Born in Germany in 1906, Goeppert-Mayer faced constant barriers simply because she was a woman. Universities flatly refused to pay her, giving her stereotypically feminine work, like figuring out what causes different colors. For decades, she was essentially a scientific nomad, following her husband from university to university, an unpaid but absolutely brilliant mind, lingering on the sidelines. It wasn't until after World War II that she began her groundbreaking work on the nucleus, the dense core of protons and neutrons that gives each atom its unique identity. She tackled a simple but profound mystery. Hydrogen, the simplest element, is the most abundant in the universe. Helium, the second simplest, is the second most abundant. But the third most common element isn't lithium, number 3. It's oxygen, element number 8. Why? Goeppert had a powerful hunch. She saw a parallel to the incredible stability of the noble gases with their full electron shells. She proposed that protons and neutrons in the nucleus also sit in shells, and that filling these nuclear shells leads to extraordinary stability. She called these magic nuclei. The magic numbers for protons or neutrons are 2, 8, 20, 28, 50, and 82. Notice that oxygen has 8 protons and 8 neutrons. It is doubly magic, making its nucleus eternally stable, which perfectly explains why it's so abundant. Calcium, with 20 protons, is another magic element, explaining why it's so common on Earth and why our bodies use it to build our bones. Goeppert-Mayer's theory was absolutely brilliant, explaining the very fabric of matter itself. Yet, when the local newspaper announced she had won the Nobel Prize in 1963, the headline actually read, "San Diego Mother Wins Nobel Prize." A rather demeaning title, perhaps, but a testament to a quiet genius who saw a hidden order in the universe that nobody else had noticed. The periodic table isn't just read left to right, but up and down as well. Elements in the same column are like family members, sharing a common heritage. Let's look at column 14, the family of carbon. Carbon is truly the element of life. It's in the 6th position, meaning it has 4 electrons in its outer shell. It needs 4 more to be stable, which is quite a lot to ask for. So instead of stealing electrons like the halogens, carbon shares them. It forms up to 4 steady, stable bonds at once, allowing it to build the long, complex chains and rings that form the backbone of every protein, fat, and sugar in our bodies. It's the ultimate connector, the social butterfly of the elements. This remarkable ability to form complex structures is actually what allows for the longest words in the English language. Proteins are long chains of amino acids, all built on carbon backbones. Biochemists have a naming system where they string together the names of all the amino acids in order. In 1964, the full chemical name for a protein in the tobacco mosaic virus was published. It's an absolute anaconda of a word, running an astonishing 185 letters long, acetylcyrrolterosyl, and so on for another 1,000 letters. It's a testament to carbon's incredible ability to build complexity. Now look directly below carbon on the table, and you'll find its closest chemical cousin, silicon. Silicon, element 14, also has 4 electrons in its outer shell, just like carbon. This similarity has made it the great hope of science fiction writers for generations. If life could be based on something other than carbon, silicon would be the obvious candidate. But silicon, for all its similarities, is definitely not carbon. It's a bigger, bulkier atom. While it can form chains, it can't bend and contort itself into the intricate rings that form sugars, which store the energy that powers life. And when silicon bonds with oxygen, it doesn't form a gas like carbon dioxide, which we can easily breathe in and out. Instead, it forms silicon dioxide, which is sand, a solid. Imagine trying to build a life form that breathes sand with every breath. It just doesn't work. While some primitive creatures on Earth do use silicon for structural support, like sea urchins with their silicon spines, it seems that carbon's unique flexibility makes it the only element truly capable of creating life as we know it. This column, this family tree, tells a fascinating story of changing character. Below carbon, the giver of life, and silicon, the foundation of our digital world, you find germanium. Germanium is the forgotten hero of the computer age. In the 1940s, scientists at Bell Labs were desperately trying to replace the big, hot, fragile vacuum tubes that powered early computers. They needed a semiconductor, a material that could precisely control the flow of electricity. The first successful device, the transistor, wasn't actually made from silicon. It was made from germanium. For a brief few years, germanium was the undisputed star, but it was temperamental and overheated easily. And silicon, the main component of ordinary sand, was, as the saying goes, cheaper than dirt. At a trade show in 1954, an engineer from Texas Instruments demonstrated a silicon transistor that could play a record while completely submerged in boiling oil, a feat a germanium transistor could never accomplish. In that single dramatic moment, the entire industry shifted. Germanium was abandoned almost overnight, and Silicon Valley was born. Germanium did all the hard pioneering work, and silicon became the icon we remember. As you continue down column 14, the family resemblance fades even more dramatically. Below germanium you find tin, a dull metal used for cans, and at the very bottom, lead, a metal that's downright toxic to life. It's a powerful reminder that while family members may share certain traits, small differences can accumulate over generations, leading to vastly different destinies. Every family has its stories, its heroes, its black sheep, and the families of the periodic table are no different. To truly understand them, you have to know the stories of the people who discovered them. The history of the periodic table is fundamentally a story of human ambition, and its main character is a wild-bearded, fiery Russian named Dmitry Mendeleev. Born in the harsh climate of Siberia, the youngest of 14 children, Mendeleev's life was one of incredible hardship, and even more incredible brilliance. After his father went blind and died, his determined mother took over a local glass factory to support the family. When the factory burned down, she pinned all her remaining hopes on her gifted son. She rode with him on horseback for an exhausting 1,200 miles across the frozen Ural Mountains to a university in Moscow, which promptly rejected him. Undaunted by this setback, she rode another 400 miles to St. Petersburg, where he was finally accepted. She died soon after, having given everything to see her son succeed. Mendeleev became a respected professor and, in 1869, did something that would change science forever. He was writing a chemistry textbook and desperately needed a way to organize the 62 elements known at the time. He wrote each element's properties on an index card and began playing a sort of chemical solitaire, rearranging them endlessly. He arranged them by increasing atomic weight, but he noticed something remarkable. Their properties repeated in a clear, periodic pattern. He laid them out in a grid, with elements of similar character lined up in the same columns. He wasn't the only one to notice this pattern. 6 other scientists independently came up with similar tables around the same time. But Mendeleev was different. He had a deep, almost intuitive knowledge of the elements, and more importantly, he was audacious. While other scientists were timid and cautious, Mendeleev was bold enough to leave gaps in his table. He boldly declared that these weren't mistakes or oversights, but placeholders for elements that hadn't yet been discovered. He went even further, predicting the exact properties of these missing elements, their weight, their density, even their color. He even gave them provisional names, using the Sanskrit word for beyond, eka aluminum, eka silicon. It was an act of incredible scientific arrogance, and it turned out to be absolutely right. In 1875, a French chemist named Paul-Émile Lecoq de Boisbaudran discovered a new element. He proudly named it gallium, after the Latin name for France. When Mendeleev read about the discovery, he immediately realized it was his predicted eka aluminum. He even wrote to the Frenchman, telling him, with no apparent justification, that he must have measured its density wrong because it didn't match his prediction. The Frenchman, understandably annoyed, carefully remeasured everything. And Mendeleev was right. The scientific world was absolutely stunned. A theorist sitting in Russia had seen the properties of a new element more clearly than the man who had actually discovered it in his laboratory. This incredible triumph cemented Mendeleev as the father of the periodic table. His table wasn't just a catalog of known substances. It was a predictive tool, revealing a fundamental law of nature. The discovery of gallium is a story about the elegant dance between theory and experiment. But it's also a very human story about pride. Lecoq de Boisbaudran, the discoverer of gallium, was a master of the spectroscope, a device invented by the German chemist Robert Bunsen. Bunsen, famous for the burner that bears his name, was a pioneer in using light to study elements. He discovered that each element, when heated in a flame, emits a unique spectrum of colored light, like a chemical fingerprint that can't be forged. This revolutionary technique allowed scientists to identify new elements with unprecedented accuracy. Lecoq de Boisbaudran was widely considered the best spectroscopic surgeon in the world, and gallium, his prize discovery, had a secret personality. It's a solid metal at room temperature, but it melts at just 84 degrees Fahrenheit. As we discussed earlier, a spoon made of gallium will vanish in a cup of hot tea. It's a prank that reveals the playful, deceptive nature that elements can have. But not all discoveries were so playful or innocent. The periodic table has a dark side, a poisoner's corridor, of elements that are masters of deception and destruction. The stories of these elements serve as cautionary tales about how chemistry can be twisted to evil ends. Cadmium, element 48, sits directly below zinc on the table. The two metals are often found together in the earth, and tragically, the human body can mistake one for the other. Zinc is an essential mineral our bodies need. Cadmium is a deadly poison. In the early 20th century, a mining company in Japan began carelessly dumping cadmium sludge into the Jinzu River. The cadmium slowly seeped into the rice paddies downstream. Local farmers, especially women, began to suffer from a mysterious and agonizing disease. Their bones softened and snapped under the slightest pressure. Their kidneys failed catastrophically. Their constant cries of pain gave the disease its haunting name, itai itai, or ouch ouch disease. The cadmium was insidiously replacing the calcium in their bones, turning their entire skeletons into brittle chalk. To the right of cadmium you find some of the most horrific elements on the entire table. Thallium, element 81, is grimly known as the poisoner's poison. It's completely tasteless, utterly odorless, and dissolves invisibly in water. The body tragically mistakes it for potassium, another essential mineral, and absorbs it readily. Once inside, it wreaks absolute havoc, unstitching proteins and causing a slow, excruciatingly painful death. Its most infamous calling card is complete hair loss. It has been the weapon of choice for spies, assassins, and serial killers throughout history, precisely because it's so hard to detect. These heavy metals are so devastatingly poisonous because they are subtle. They're not violently reactive like sodium. They can sneak deep into the body, expertly mimicking essential nutrients before they begin their destructive work. They're the imposters of the periodic table, the elements that betray your body's trust. The elements have not only been weapons of murder, but weapons of war, dramatically shaping the course of global conflicts. World War I is remembered for its brutal trench warfare, but it was also the first truly chemical war. It began with bromine, a halogen that causes searing, blinding tears. The French first lobbed bromine shells at the Germans in 1914, but the gas proved largely ineffective in open air. The real architect of chemical warfare was a German chemist named Fritz Haber. Haber was an undeniable genius, a man who could have been one of the greatest saviors in all of human history. Around 1900, he figured out how to pull nitrogen, which makes up 80% of our atmosphere, out of the air and convert it into ammonia. This revolutionary process made the mass production of artificial fertilizers possible for the first time. Haber's invention has been credited with feeding billions of people around the world, saving countless lives from starvation. He rightfully won a Nobel Prize for it. But Haber's motives were not entirely humanitarian. He developed the process primarily to help Germany create nitrogen-based explosives for warfare. When World War I broke out, he eagerly volunteered to lead Germany's poison gas division. He abandoned bromine and turned to its nastier cousin chlorine. Chlorine viciously attacks the lungs, causing victims to essentially drown in their own fluids. Haber personally directed the first successful gas attack in history, which left 5,000 French soldiers scarred, dying and gasping for air in a trench near Ypres. His wife, Clara Immerwahr, also a brilliant chemist in her own right, was absolutely horrified by his work. She begged him repeatedly to stop. He coldly ignored her pleas. After he returned triumphantly from Ypres, he threw a lavish party to celebrate his devastating new weapon. That very night, Clara took his army pistol, walked quietly into the garden, and shot herself in the chest. Haber left the next morning to direct even more gas attacks on the Eastern Front, seemingly unmoved. Haber's is one of the most tragic and complicated legacies in all of science. He was a Jew who converted to Lutheranism to advance his career, a fierce patriot who developed horrific weapons for Germany, and a man whose scientific brilliance was used for both immense good and unimaginable evil. The Nazis later exiled him for his Jewish heritage, and he died in 1934, broken and alone. In a final, deeply horrifying twist of irony, the chemical company he had worked for later manufactured Zyklon B, the insecticide gas used to murder millions of people, including some of Haber's own relatives, in the concentration camps of the Holocaust. Warfare is also fundamentally driven by metals. During World War I, Germany's most feared weapons were its Big Bertha siege guns, massive cannons that could hurl enormous shells for miles. The intense heat generated by firing these guns repeatedly warped their steel barrels, making them inaccurate. The famous Krupp Armament Company found an ingenious solution, spiking the steel with molybdenum. Molybdenum has an incredibly high melting point, making the barrels far more durable and accurate. But Germany had absolutely no domestic supply of molybdenum. The only significant known source was a mine in the Rocky Mountains of Colorado. A German-owned mining company waged a secret, ruthless war to seize control of the mine, sending in claim jumpers to harass the American owner, openly threatening his family and even throwing him off a cliff at one point. He miraculously survived, but the Germans eventually got their Molly be damned, and for years afterward, they shelled Paris with guns made stronger by an element secretly mined deep in America. In World War II, the coveted IT metal was tungsten, which sits directly below molybdenum on the table. It's even harder and has an even higher melting point. The Nazis desperately coveted tungsten for armor-piercing missiles. The primary supplier was supposedly neutral Portugal. The Portuguese dictator, Antonio Salazar, cynically played both sides, selling thousands of tons of tungsten to both the Allies and the Axis powers, cleverly leveraging his country's near monopoly to make immense profits. Tragically, much of the gold the Nazis looted from their victims, including gold fillings pulled from the teeth of gassed Jews, was laundered through Portuguese banks to pay for the tungsten that fueled the German war machine. The story of the elements isn't just written on Earth, it's written in the blazing hearts of stars. For centuries we naively believed that the elements have always existed, that they were simply created alongside the universe itself. But in the 1950s, a handful of brilliant astronomers, including a brilliant and eccentric man named Fred Hoyle, realized that stars are actually the great forges of the cosmos. The universe began as an enormous slurry of hydrogen, with a bit of helium mixed in. Gravity slowly pulled this hydrogen together into the first stars. The immense pressure and heat inside a star's core fuses hydrogen atoms together to form helium. This is the process that powers every single star twinkling in the night sky, a slow, steady burn that can last for billions of years. But when a star finally runs out of hydrogen fuel, things get dramatically interesting. The star, desperate for more fuel to keep burning, begins to fuse helium into heavier elements, carbon, oxygen, all the way up to iron. Each new stage of fusion buys the star a little more time, but the end is rapidly approaching. Iron, element 26, is the absolute end of the line. Fusing iron doesn't release energy like earlier fusions. It actually consumes it. An iron core is essentially a star's death sentence. So where do the elements heavier than iron come from? Gold, lead, uranium, and all the rest. They come from the most spectacular, violent events in the entire universe: supernovae. When a massive star finally runs out of fuel, it collapses catastrophically under its own immense gravity in a matter of mere seconds. Then, it rebounds in an absolutely cataclysmic explosion of unimaginable power. For one glorious month, a single supernova can actually outshine an entire galaxy containing 1 billion stars. In this cosmic inferno, so many particles collide with so much incredible force that they overcome the energy barrier of iron. They fuse onto iron nuclei, creating every single element and isotope, all the way up to uranium, and spewing them dramatically across the galaxy in a spectacular cosmic fountain. One such massive explosion, about 4.6 billion years ago, seeded our particular corner of the cosmos with all the elements that would eventually become our solar system, our planet, and ultimately us. As the great astronomer Carl Sagan so beautifully and poetically put it, we are all star stuff, literally forged in the hearts of dying stars. This massive cosmic dust cloud gradually coalesced over millions of years, with our sun forming at its center. Lighter elements were blown outward to the outer edges, forming the gas giants like Jupiter and Saturn. Jupiter, the largest planet, is essentially a failed star. If it had been just a bit more massive, it might have ignited fusion in its core, and we would be living in a binary star system instead. Even as a planet, its immense gravity and crushing pressure create exotic, almost unimaginable forms of matter, like vast oceans of liquid, metallic hydrogen, deep in its interior. Scientists even theorize about neon rain, actual droplets of liquid neon falling through its upper atmosphere, lighting up the Jovian sky with brilliant streaks of crimson light. The rocky inner planets, including our Earth, formed from the heavier elements closer to the Sun. As the molten Earth churned and bubbled, dense iron gradually sank down to form the core. Lighter elements rose up to form the crust we stand on. But how do we actually know this history? How do we know the true age of the Earth? The answer lies in the slow, steady, utterly reliable decay of radioactive elements. The heaviest elements, like uranium, are inherently unstable. Over billions of years, uranium slowly breaks down into lead through a series of intermediate steps. By carefully measuring the ratio of uranium to lead in the oldest rocks on Earth, a determined and meticulous scientist named Claire Patterson, working in the 1950s, was able to calculate the age of our planet with remarkable precision, 4.55 billion years. But Patterson's painstaking work had a completely unintended consequence. To get an accurate measurement, he had to create an ultra-clean laboratory, completely free from any trace of lead contamination. In doing so, he made a horrifying discovery. Our entire planet was covered in a fine, pervasive dust of industrial lead, coming primarily from leaded gasoline. His profound horror over this widespread contamination turned him into a passionate activist, and his tireless crusade is the main reason we no longer have toxic lead in our paint or our gasoline today. The elements don't just tell us the history of our planet, they tell us about the dramatic cataclysms that have shaped it. 65 million years ago, the dinosaurs mysteriously vanished from the Earth. In the 1970s, a father-son scientific team, Luis and Walter Alvarez, were carefully studying limestone deposits from that particular era. They found a thin, completely unaccountable layer of clay that contained 600 times the normal level of the element iridium. Iridium is extremely rare on Earth's surface. Most of it is locked away deep in our iron core, but it's relatively common in asteroids. The Alvarezes boldly proposed that a massive asteroid, roughly the size of a metropolis, struck the Earth with devastating force, throwing up an enormous cloud of iridium-rich dust that blotted out the sun for years and caused a catastrophic mass extinction. The later discovery of a 100-mile-wide crater on the Yucatan Peninsula, dating to exactly that time period, seemed to definitively prove their theory. The quiet, patient testimony of a single element had solved one of the greatest mysteries in all of Earth's history. The stories of discovery are filled with moments of brilliance, but also with mistakes, some of them truly monumental. Emilio Segre, the man who finally hunted down the elusive element 43, technetium, made one of the biggest blunders in the entire history of nuclear physics. He was working closely with the legendary physicist Enrico Fermi in 1934, when Fermi proudly announced he had created the very first elements beyond uranium on the periodic table. It turned out Fermi had actually been the first person to successfully induce nuclear fission, literally splitting the uranium atom apart, and he hadn't even realized what he'd done. Years later, Segre, having learned this lesson perhaps too well, was asked to analyze a mysterious sample that was thought to be a new transuranic element. He quickly dismissed it as just another ordinary fission product, nothing special. That sample actually contained neptunium, the first true transuranic element ever created, and the colleague who had asked for his expert help, Edwin Macmillan, went on to win a Nobel Prize for its discovery, while Segre watched from the sidelines. But perhaps the most famous mistake in modern chemistry belongs to the man many consider the greatest chemist of the entire 20th century, Linus Pauling. In the early 1950s, the race was dramatically on to discover the structure of DNA, the molecule of life itself. Pauling, already a two-time Nobel laureate and scientific superstar, was the overwhelming odds-on favorite. Working with incomplete and sketchy data, he rushed to publish his model first. He confidently proposed that DNA was a triple helix, with the phosphate backbone at its core. Across the Atlantic, two young, relatively unknown scientists, named James Watson and Francis Crick, somehow got a copy of Pauling's paper. They were absolutely stunned by what they read. They had actually built the exact same model about a year before, and had been firmly told by their colleagues that it was completely wrong. They instantly knew Pauling had made a fundamental, elementary error. The negatively charged phosphate groups packed together in the core would violently repel each other, literally blowing the molecule apart. It simply couldn't work. Knowing that Pauling would soon realize his embarrassing mistake, they frantically scrambled to build a better model. Using a crucial piece of X-ray crystallography data from their colleague Rosalind Franklin, they built an entirely new model, a graceful double helix, with the phosphates safely on the outside. They published their groundbreaking work in April 1953, narrowly beating Pauling to the greatest biological discovery of the century. Pauling, to his incredible credit and grace, admitted his mistake openly and enthusiastically championed their correct model. The periodic table isn't just a tool for chemists and laboratories. It's been a source of inspiration for artists as well. The poet Robert Lowell, one of the great mad geniuses of his time, suffered from completely debilitating manic depression that tormented him for decades. His life was an exhausting, chaotic storm of brilliant poetic creation and self-destructive behavior that hurt him and everyone around him. In the 1960s, he began taking a new drug, a remarkably simple salt of the element lithium. Lithium is a powerful mood stabilizer. It works by essentially resetting the body's internal clock, the circadian rhythm. In people with manic depression, this internal clock runs completely wild, independent of the sun and the seasons, leading to euphoric, destructive highs and crushing, suicidal lows. Lithium helps regulate the specific proteins that control this clock, gently tethering the mind back to a normal, healthy 24-hour cycle. The drug genuinely transformed Lowell's chaotic life. He became stable, calm, able to function normally. But his poetry changed as well, in ways he wasn't entirely happy about. It grew less polished, less wildly inspired, more ordinary. He once confessed to his publisher, with deep sadness, "It's terrible, Bob, to think that all I've suffered, and all the suffering I've caused to those I love, might have arisen from the lack of a little salt in my brain." The story of Lowell and lithium is a deeply poignant reminder that our highest faculties, our creativity, and even our madness, are ultimately rooted in the simple chemistry of the elements coursing through our bodies. As we reach the very bottom of the periodic table, the elements become increasingly strange and fleeting, existing for mere fractions of a second. These are the man-made elements, painstakingly created one atom at a time in massive particle accelerators. The discovery of these elements became a new theater for Cold War rivalry, a fierce competition between a team at the University of California, Berkeley, led by the brilliant Glenn Seaborg, and a Soviet team at a secretive lab in Dubna, Russia. For decades, they battled intensely for priority, for the right to name a new piece of the universe and claim it for their country. The Berkeley team patriotically named elements after their university, berkelium, and their state, Californium. The Soviets named one after their lab, dubnium. In a rare moment of scientific magnanimity and international goodwill, the Berkeley team named element 101 Mendelevium, in honor of the great Russian chemist Dmitry Mendeleev. But the truce didn't last long. The bitter dispute over who actually discovered elements 104, 105, and 106 dragged on for an exhausting 30 years, continuing long after the Cold War itself had ended. In the end, Berkeley won the right to name element 106 Seaborgium, after their beloved leader Glenn Seaborg, making it the only time an element has ever been named for a living person. And what about the future of the periodic table? Where does it actually end? The elements get progressively more unstable as they get heavier, with shorter and shorter lifespans. But physicists theorize about an intriguing island of stability, a cluster of super-heavy elements around element 114 that might be surprisingly long-lived, perhaps stable for days or even years, instead of milliseconds. Reaching this theoretical island is one of the great quests of modern physics. But there may actually be a hard, absolute limit to the periodic table. Richard Feynman, another brilliant physicist, calculated that around element 137, the fundamental laws of physics as we currently understand them begin to completely break down. The innermost electrons of such a massively heavy atom would theoretically have to travel faster than the speed of light to remain in orbit, which Einstein's theory of relativity absolutely forbids. At this point, the irresistible force of quantum mechanics would meet the immovable object of relativity head-on. What happens then? Honestly, no one really knows. This undiscovered element, 137, is sometimes playfully called Feynmanium by physicists. It represents the very edge of our knowledge, the point where our detailed map of the universe simply goes blank and we enter unknown territory. The periodic table we all know, the familiar castle shape, is actually just one possible arrangement among many. Scientists have designed over 700 creative variations over the years: spirals, helixes, pyramids, even circular designs. And our fundamental understanding of what an element even is continues to expand and evolve. Scientists can now create fascinating superatoms, carefully designed clusters of atoms of one element that mimic the chemical properties of another element entirely. 13 aluminum atoms can band together and act just like a single atom of bromine, fooling other atoms. They're also exploring quantum dots, virtual atoms made not of a single nucleus, but of a collective of thousands of atoms, all acting as one unified entity, The story of the elements is far from over. The periodic table is not a finished work gathering dust in a museum, but a living, breathing document. A story that is constantly being written and rewritten by scientists around the world. It is a powerful testament to human curiosity, to our seemingly unending quest to understand the world and our place in it. From a simple disappearing spoon at a dinner party to the violent birth of stars across the cosmos, from the poison hidden in an assassin's vial to the simple salt that calmed a tortured poet's mind, the elements are the characters in the epic, ongoing story of our universe. And it's a story that is literally all around us and inside us, patiently waiting to be read and understood. After a journey like that through Sam Kean's The Disappearing Spoon, it's genuinely hard to look at the world in quite the same way. What I find so powerful and transformative about this book is how it takes something we all thought we knew, that boring chart from chemistry class that seemed so abstract, and transforms it into something deeply personal, alive, and fascinating. It's a profound shift in perspective that stays with you. The greatest lesson, I believe, is that science is absolutely not a collection of cold, hard, impersonal facts locked away in textbooks. It is fundamentally a human endeavor, driven by the exact same passions, flaws, rivalries, and flashes of brilliant inspiration that define all of human history. We see the bold ambition of Mendeleev, risking his entire reputation on a daring prediction about elements that didn't even exist yet. We see the tragic, conflicted patriotism of Fritz Haber, whose genius both fed the world and gassed it with poison. We see the quiet, persistent perseverance of Maria Gokut-Meyer, a brilliant mind consistently overlooked and unpaid for decades simply because she was a woman in a male-dominated field. These aren't just dry stories about scientific discoveries, they are profound stories about what it truly means to be human. The periodic table becomes a mirror, reflecting our capacity for incredible discovery and terrible destruction, for selfless generosity and selfish greed, all at once. Kean reminds us that the world around us is so much more intricate, interconnected, and fascinating than it appears on the surface. We walk around every single day, breathing air, drinking water, using technology, and rarely do we pause to consider the incredible, epic stories of the individual atoms that make it all possible. The oxygen we're breathing right now was forged in the fiery heart of a dying star billions of years ago. The silicon in our phones was at the center of a fierce scientific rivalry that ultimately created the entire modern world. The lithium in a battery might be chemically identical to the element that saved a tormented poet's life and sanity. The book gives us a completely new lens through which to see the hidden wonder in the mundane and ordinary. It connects us to the grand cosmic story of the universe, spanning billions of years, and at the same time, to the intimate, personal stories of the flawed, brilliant people who shaped our understanding of it all. So how can you actually apply this? What can you take away from this today and use in your own life? It's actually quite simple and accessible. The next time you encounter the periodic table, whether it's in a textbook, on a poster, or just a picture online, don't just see it as a scientific tool or a chart to memorize. See it as a vast library of fascinating stories waiting to be discovered. Pick an element, any element at all. It doesn't have to be a famous, glamorous one like gold or uranium. Pick something obscure and overlooked, like dysprosium or praseodymium or ytterbium, and just get genuinely curious about it. Spend just 5 minutes looking up its unique story. Who discovered it, and under what circumstances? Where does its unusual name come from? What strange, completely unexpected role has it played in human history or technology? By doing this simple exercise, you're not just passively learning a random fact to forget later. You are actively practicing the very essence of what this book teaches, that curiosity is the fundamental engine of all discovery, and that everywhere you look in every direction, there is a fascinating story waiting to be found and appreciated. You begin to see the world not as a boring collection of static objects, but as a dynamic, interconnected web of histories, all woven together. That's a genuinely powerful way to live, to be constantly surrounded by wonder and possibility. You start to realize that the history of the entire world isn't just locked away in dusty history books. It's written in the very atoms that make up the world itself, the chair you're sitting in, the air you breathe, the device you're holding. That was a summary of The Disappearing Spoon by Sam Kean. We've touched on some of the most captivating, entertaining tales today, but I'll be completely honest with you. A summary like this is just a glimpse through a keyhole at a much larger room. The real magic, the real depth, happens when you open the door wide and explore all the rooms yourself. The actual book is filled with hundreds of other equally fascinating stories, each one as compelling and surprising as the last. This summary is designed to help you decide if this book is genuinely worth your valuable time. If anything we've talked about today has sparked even a little curiosity in you, I wholeheartedly encourage you to grab a copy and dive in. Reading it isn't just about learning dry facts. It's a genuine experience that can change the way you see the world and appreciate the rich history woven into every single thing around you. The link to the book is in the description below. Also, if you found this journey valuable and entertaining, please take a quick moment to click that like button and subscribe to our channel. That way, you won't miss our next exploration into another potentially life-changing book. Let's continue to grow, learn, and discover together.